Hello, this is a recorded version of the ECMFA keynote that I gave at STAF in Toulouse last week, entitled Is Bidirectionality Important? So here's my rough plan. I'm going to start off by talking about what important should even mean to us. Many of you I know perfectly well what bidirectionality is, but I think I had better explain that somewhere along the way. And in order to address the question of whether it's important, I'm going to have to discuss how it relates to the problems that software engineering faces, and I'm going to spend a fair bit of time discussing what I think those problems are. And of course, in the end, I'll answer the question, both with respect to our needs now and with respect to software engineering's needs in the future. Now, it probably won't really surprise anybody what answer I'm going to come up with, but you might perhaps have been wondering if you're aware of a thing called Betteridge's law, which relates to newspaper headlines and the like, which are posed in the form of Boolean questions. So here are a selection that I grabbed off the BBC News site on one particular day, and let's just pick out a few where the answers are particularly clear. Will there be a Brexit dividend? Well, no. There's one Donald J. Trump who raised the question of whether Canadians were smuggling shoes. A particularly worrying one is whether we're in for a beer shortage this summer. Now, that one I had to click on and read, or watch as the case may be, but it turns out that the answer is no, at least assuming that you have a proper definition of what beer is. It's the stuff that depends heavily on food-grade carbon dioxide, which we may be in for a shortage of this summer. Fortunately, however, my title is not a newspaper headline, and so I'm not bound by this convention. Now I'm in an after-lunch slot, and I think it's appropriate that I take a philosophical rather than a technical approach to the subject, although I do certainly hope that what I say will have implications for both my technical work and yours in the future. I'm aiming to be thought-provoking, even provocative, and therefore I said in The Real Thing that I only wanted brief clarification questions as I went, and substantive questions could wait to the end. But hey, in a recording I don't need to say that, because you can't interrupt me even if you wanted to. Okay, so what do we mean by important? Well, I'm not going to give a dictionary definition. I'm going to give you my own and say I think that a thing is important if it deserves attention. And why does it deserve attention? Because we think that if we give it attention, we may make a positive difference. So there are two different judgments involved there. One is the estimation that giving the thing attention may make a difference, and the other is the value judgment that it may make a positive difference. And specifically to us, a thing being important indicates that it deserves attention from software engineering researchers, and I'll return at various points to roles other than software engineering researchers. I've been fortunate this year to be on sabbatical. That in UK terms means that I've had a year in which I haven't had teaching and administrative responsibilities for my employer, the University of Edinburgh, and instead I've been able to devote my time full-time to research. And they give us this privilege once every 9 years in order to encourage us to lift our noses up from the grindstone and ask big questions such as, what is it all for? Why am I researching this particular subject? What does it have to do with things that are actually important, things that I actually care about? And should I continue to do it, or should I do something completely different? And this is a wonderful opportunity. But in an audience of people who maybe are not all native speakers of English, I'm not sure whether this expression, to lift one's nose up from the grindstone, is particularly well known. So the idea is that putting your nose to the grindstone indicates working hard at something that you're looking at from close quarters, perhaps without much of a view to the big picture, and perhaps without very much pleasure. So it's an appropriate metaphor to use here. But one of the things that I've been doing in my sabbatical is spending time out of the office. For example, in the National Museum of Scotland, which is only a short walk from my office, as it happens. So this is a grindstone that I found there. In particular, this is a saddle quern. It was found in North Uist, off the west coast of Scotland, and it dates from about 5,000 years old. And It's a tool, and don't push me very far on this because I don't know very much about it, but the development of such tools, and by the way they are developed, not just found, so for example the surface is pecked probably, which indicates that it's made rough to optimise its performance at its job, which is to grind grain into flour, in this case barley grains. And so typically a woman would be kneeling in front of this thing, grinding grains into flour, and the development of this kind of technology and the ability to bake flour and in the process to get much more nutritional value out of it was, as I understand it, very important in the development of early agricultural human societies that were settled in villages rather than purely nomadic. And thereby changed the relationship between humans and the world, and between humans and one another in their societies. So it's an important kind of tool. Similarly, a piece of software is a tool, and similarly it isn't just a tool for an individual to use for their own benefit. It's a tool which enables us to reconcile interests that are not perfectly aligned in order to get more benefit for the group as a whole than the individuals could get if they just worked as individuals. So it's the cooperation is both to build and to use the tool. Software, we may say, changes the world, and at the same time it changes human relations. And that's the sense in which software is important. It's not simply that software computes a function over an argument, however much that may sometimes be a useful abstraction of what it does. So, once upon a time, of course, there was no software. The people who used that quern didn't have much in the way of software. But even once there was software, for quite a while it wasn't really important. So in the early days of software, it was relevant, I would say, only to these top two levels of the Maslow hierarchy of needs. For example, it was used for space travel, and it was used for looking after rich people's money. But for most people in the world, in most circumstances, it didn't really have much impact on their lives at all. That changed quite rapidly. So these days, software mediates food production and warmth and cooling, and of course health and healthcare, and I'm sure many of us, like myself, have friendships that are important to us and that simply could not exist without software enabling our communication. So software is now important throughout the Maslow hierarchy of needs, and we can't possibly go back any more than flour could be uninvented. It has changed the nature of human society irrevocably. So software is important these days. You may be wondering, does she really mean all software is important? Is Minecraft important? Well, no. The kind of software I'm talking about is the software that changes our relationship with the world and our relationship to one another, and in the process involves reconciling different needs. So what's important for us as software engineering people is to help to provide software that's good in its context. And the reason for that is that we want to let other people get on with other important things. So this one on the left is a rotary quern. It comes from about 3,000 years later and apparently grinds corn about twice as fast as the one I gave in the first place, grain I should say. They could maybe have done with a bit more Moore's law in those days. But it had various other benefits, for example involving fewer skeletal deformities for the people using it. And on the right we have a Roman quern, which was for heavy-duty use. It's made of very hard volcanic rock. It dates from about the same time as the one on the left, about 3,000 years after the first one I gave. And I think the important thing about this was that it was grinding grain for armies, so it had to be used day in, day out. So different tools for different contexts and different requirements of use. Let's turn now to in what ways software and its engineering need improvement. Do they need improvement? So we're going to talk about what's needed for today's requirements and also about what we think will be needed in the long term. So in order to think about today's requirements, let's recap how we got here. In the beginning was the software crisis. The idea of the software crisis may actually, to a younger members of an audience may require some explanation. When I came into software engineering, and a few years later into lecturing on software engineering, everybody knew about the software crisis. You could stand in front of a class full of students and ask them who has heard of the software crisis, and all the hands would go up. And in fact, in some cases, that would be why students were there. They were intrigued by it and they wanted to help contribute to solving it. These days, if you stand in front of a group of students, they haven't heard of the software crisis, which is very interesting. This quotation comes from a report on the 1996 Dargstuhl on the history of software engineering. The writer is Peter Shapiro. And this was talking about 30 years since the early NATO conferences in which the term software crisis was coined. It turns out the term software engineering, by the way, was coined earlier than the NATO conferences, even though it's often said that it was coined at those conferences and has even been said by me. So as you see, in 1996, it was widely agreed that there was a crisis in the sense that it was understood that it was not possible to reliably develop large, complicated software systems that would do what they were supposed to do and develop them to time and to budget. And that had been the case for 30 years. Although there had been some technical improvements, the requirements of software had improved even faster, and the steady state that people were worried about it and it couldn't be done had persisted throughout that time. So the software engineering crisis wasn't a thing that might have happened but didn't. It really did happen. It was a huge problem. And yet these days students haven't heard of it. Now that's because fundamentally it's gone away, and that's fantastic. So let's take a look at why that has happened. So I love using Google Ngrams for this kind of thing, but I should emphasize that they're really not science. So these are pictures, and the pictures are useful particularly when they reinforce your prejudices in whatever way. So this is a representation of the prevalence of the phrase software crisis in a corpus of books that Google Ngrams examine for the purpose. And you can see here rather nicely that the term software crisis rose steadily from the early days of software engineering up to a peak in about 1990, and then has been steadily falling ever since. And that matches with the idea that in the early 90s students all had heard of the software crisis, and these days they haven't. So in order to think about what's contributed to the fall of the software crisis, we may want to look for terms that have risen at the same time as the software crisis term has fallen. And here are two which may appeal to this audience. It's always slightly dodgy, of course, picking exactly what terms to use, but I think it's reasonable to say that model-driven development, in particular the idea that using abstract representations of the design of a system is an important technique to use, has indeed been important. Agile development you may be suspicious of, because as you see it rises up rather later than the software crisis begins to fall, but that's really partly an artifact of the term one uses to search for. Extreme programming is harder to search for, but predated agile development and introduced some of the same ideas. So fundamentally I think what's going on here is better understanding of abstraction and better understanding of the importance of limiting the cost of change, and those two things between them have been very important, and I'll say a little more about that in a moment. People who know me well would not expect me to pass by without pointing out some terms that by this measure do not appear to have contributed to the fall of the software crisis. So what we've done, I think, is to make some progress on this eternal problem of software engineering, which is the perception that there's a balance between dependability and capacity, between building software better and building it cheaper and faster, which in software engineering turn out to be more or less the same thing. So I've been able to represent them as one end of the seesaw here. In the early days of software engineering, these two things did appear to be in opposition. You could either have a high ceremony process in which you did things slowly and carefully and you had a long testing phase, for example, or you could hack it and you paid your money and you took your choice, and these things were in opposition. And one of the ways in which we've made progress is to realize that they don't have to be in opposition. So testing, for example, doesn't have to be a thing that takes a huge amount of effort, where you have to start by building your own testing framework, and then you put all the testing in a phase at the end of development where it's liable to get squashed when the customer is screaming for the software. Instead, you can do it earlier, you can make use of the development of tests to clarify requirements, you can use widespread publicly available frameworks such as JUnit, and all in all you can make testing be a thing which contributes both to the dependability of the software that you're building and to your ability to build it fast and incorporate changes in it as required fast. So that's great. And there are many other examples. So what we can say is that, in effect, we have fastened some helium balloons to this seesaw so that instead of one side going up and the other side going down, both sides go up simultaneously. And I would characterise the two main advances in these two categories. So one is the overall idea that quality is free. This is a title of a book by Philip Crosby. In software engineering, it captures the idea that certain kinds of improvement to the quality of software also improve your ability to deliver it, especially by improving your ability to continue to deliver changes to it. And on the other hand, we have better technology in very many different aspects. So I mentioned testing frameworks already. We also have better languages, programming languages, modeling languages. We have better tools, type systems. We have better model checking tools and theorem proving tools, although they're only used in small niches at the moment. And importantly, we have better hardware on which to run these things, and so stuff that would have been dismissed as impractical for performance reasons 30 years ago are now becoming routine. So this is great. But another of the things I've been doing on my sabbatical is trying to get to grips with David Allen's getting things done methodology, and a thing he says a lot is the better you get, the better you better get. And that's very much true for software engineering. The better we get at delivering highly dependable software fast, the more need for software and for changes to software comes out of the woodwork. Now let's spend a moment looking at where we've made progress in the context of the software lifecycle, in scare quotes. So let's see what's been done and what remains to be done. It's interestingly always the case that problems with software engineering show up in the areas I've put above the waterline here, at the requirements phase and at the maintenance phase. And that's not surprising, of course, because that's the point where software meets the people who actually care about having the software, namely the users and the customers. But what's intriguing is that we haven't really made revolutionary developments in either of those areas, in either requirements engineering or in maintenance. What's happened instead is that we've made many point improvements in the part of the process which is below the waterline here, and we've also got very much better at repeating that swoop from requirements to maintenance much faster than we used to be able to. And so we're able to say, okay, we know we won't gather requirements absolutely perfectly and then go through this process of analysis, design, implementation, testing and deployment just once. Instead, what we'll do is we will assume that it's a fact of life that requirements will change, or we will find that we didn't capture requirements perfectly, and so we'll have to go through that swoop multiple times. And even if we did capture requirements perfectly at one point in time, they would change. So on we go. You can see all of the things we've done, if you squint, as advances on the really fundamental problem of software engineering, which is just that there is too much information around to fit into a single human brain. I think these are fundamentally all the same idea, really. So we've got abstractions that we use now on every level. So we have come to understand that it's important that individuals who are going into software development be people who are comfortable working with abstractions, and we've talked earlier on at STAF about how to teach people to do that. We've got languages which make better use of abstractions. We've got verification techniques. We make better use of interfaces these days, for example, for unit testing. We are getting much better at separating concerns, for example, into different models. And I'll have a thing to say in a moment about what models are, but for now let me just say that models are not necessarily diagrammatic. Text files are models too. And you can even see the kind of sequentialization that we do, for example using slogans like "you ain't gonna need it" and doing bounded small releases, as being another kind of abstraction, a sort of sequential abstraction. So this is all about human capability. All of these things are about getting chunks of processing done within the limited capacity of an individual human brain. Now there's a lot more to be done, and especially to do with combining the different kinds of abstraction I've listed here, and this is why model-driven development plus agile development is often held to be a difficult sum to solve. The downside of this is that splitting the overwhelming amount of work into chunks necessitates integrating those chunks, and that has been a problem since the beginning and remains a problem now. So in the early days, the observation of the famous mythical man month was that if you added people to a late software engineering project so that you could split the work into more chunks and parcel those chunks out to the new people, the result was often to make the project later, because the communication overhead, the integration of the chunks that were in those different people's heads, imposed more cost than the benefit that you got from the work that those people did. In the bad old days, it used to be a commonplace that these large software engineering projects, most of which would fail in the days of the software crisis, would have long, sometimes years-long, integration phases in which people belatedly found out that it was difficult to integrate the chunks that had been carefully developed separately. We can see paying off technical debt in sprint-based projects as being a process of integrating the sequential chunks, which are those sprints. And coming closer to our own hearts here at STAF, managing projects that involve multiple DSLs, not just one, is still a problem, especially where the DSLs really are close to independent. For example, they're being used by different people with different concerns. It's hard to maintain copies of the same information. So, oh dear, we might say, difficulty is preserved, there ain't no such thing as a free lunch. And yet, every one of us is the descendant of countless ancestors who did not starve, so maybe we don't need a free lunch. Maybe we can find our way around this difficult issue. So what we want is a systematic way to control the integration of separated concerns, and that is what bidirectionality is all about. So I think there are three parts to the essence of bidirectionality. We'll start with a model. Well, in fact, we'll start with more than one model. And our models, at least two of them, have to have the properties that they are simultaneously live, I'll say some more about that in a moment, and that they're not orthogonal. And if we've got all three elements here, then we are, I claim, in a situation which is essentially bidirectional. So let's look at these a little more carefully and start off by asking, what's a model? Well, everything's a model, which is good because that means we can work with everything. Here's my favourite one-sentence definition of a model. A model is an abstract, usually graphical representation of some aspect of a system. Now, I've been using this definition for many years now, and I'm very glad that I put that word usually in there, because increasingly graphical models attract suspicion in many quarters, and it's important to be able to point out that actually a lot of the time for us in the model-driven development community, the fact that a model is graphical really doesn't matter at all. All the same issues come up if you consider textual models, and if people are more comfortable with those, then we can do that. The important thing about a model, arguably, is that it has a boundary. There's a sense in which a piece of information may be inside the model or it may be outside the model, and that's the key abstraction element here. So everything's a model, but somehow thing is a key there. So for example, UML models are models, of course, so are database schemas, so are things that might or might not be expressed in standard modelling languages, such as a map of the user's navigation between screens, but also a bunch of Java code is a model, and so is a bunch of JUnit tests. So a model will be created and will have the role of supporting the work of a particular group of people, and ideally a model should record all and only the information that those people need in order to do their work. And so having multiple models is simply a consequence of separation of concerns. Now, I said that the models had to be live, and what I meant by that was simply that they should not be dead yet. So a model should be liable to be changed in future, liable to have a decision recorded in it at some time in the future. We could also say not fossilized yet. Yes, that's all I want to say, I think. So let's contrast that with something. You could imagine an idealized refinement-based development in which a model might die when you turned your attention to a different model that might be derived from that first model, when the different one was then thrown over the wall and the original model was of no further use. So, for example, you could imagine working in a project where you first write the JUnit tests, and then you freeze them, and then you write the code from those JUnit tests, and you never need to change the JUnit tests ever again. Well, you could imagine it, but I bet you couldn't actually take part in such a project, because in practice life is not ideal, so you normally would expect to have to change the tests after you have started to write the code, and vice versa. However, there's no problem with having several live models simultaneously if the information that they record is completely independent. If it isn't completely independent, then we have all three factors and we're in a bidirectional situation. So what's going on now is the idea that a change in either model may or may not necessitate a change in the other. So when something changes in the JUnit tests, we may or may not have to update the Java code. And it's important to say that we may not, and also important to observe that some changes that we might make in response to a change in one model are better than others, and we want to have some kind of control over that choice of how to restore the good situation after a change. So, for example, it might be that we add a new test to our JUnit test class, and the Java file doesn't pass that test yet, and so now we want to change our Java code so that it passes the test. Or it might be that we change the interface to a particular method, and that means we have to update the test so that they call that method correctly. And in some cases there'll be no choice about how to propagate that change, and in other cases there'll be lots of choice. Now, there is a very special case in which we always have to make a change on one side in response to a change on the other, and where there's no choice about what change to make. That situation is very special. That's where you have a bijective consistency relation, a single model on one side that's consistent with any given model on the other. And it's very special because effectively what that says is that the two models represent the same information but in a different format. And typically that's not the case, because you typically wouldn't bother to maintain two models that contained exactly the same information. So, for example, if you add a JUnit test, there are typically very many different ways of updating the Java code so that it will pass the test. So the two tasks of bidirectionality, and notice that I'm not yet talking about automation, are on the one hand to check whether all is well, and on the other hand, if not, to fix it. So choices that we have to make include, most importantly, how much to articulate of what we mean by all is well, and I'll give some examples in a moment. And then, having done that, we get to choose how we're going to get that fixed. It might be a purely human process, or it might be a purely automatic process by a bidirectional transformation, which is our word for an artifact that automates these tasks, or by both in combination. We have choices about whether we're going to restore the all is well situation by changing one model or by changing both. And we also have a whole family of choices about which I'm not going to have much more to say today, about what information we want to maintain in order to do all this. So we probably are going to need to maintain, of course, at least the information that's in the two models, or more than two models, but we may also want a variety of other information, such as traces, or history, or deltas, or intentional information about edits, or various other pieces of information that might help us to do a better job, either of checking that all is well or of working out the best way to fix it if it isn't. Before we go on and look at the different things that all is well might be, let's quickly address why we even need a term bidirectional transformation at all, because after all, checking and fixing things automatically sounds like a job for a program. So is a books different from a program? Well, yes and no. So a books is a special kind of program, and it is going to record in one artifact both what it means for all to be well, that is, we say, for the models to be consistent. We use this term consistent as a label for the relation that models satisfy, if and only if we want to say all is well. And at the same time, in the same artifact, a books records how to restore consistency in either direction. Now, we could record these things in separate programs in our favourite programming language, but because the tasks are very tightly coupled, it pays to integrate their automation into one artifact. It helps us to avoid duplication of information, for example, information about the structure of the models that are being checked for consistency and having their consistency restored. And on the other hand, it makes it easier to guarantee sensible, predictable or dependable joint behaviour of the automated versions of these tasks. So, for example, if we consider the simplest possible case of a bidirectional transformation between two models, which is going to completely automate the restoration of consistency, then one sensible property that we would like to have is that if we restore consistency using it, then having done that restoration of consistency, we ask the same books whether now all is well, we would expect it to say yes. In other words, we would expect the consistency restoration actually to succeed in restoring consistency. And that's the property that we describe as correctness. And another property that we normally want is called Hippocraticness, and that says that if you take two models which, according to this books, are consistent, so it says yes, all is well if you ask it, and then you ask the very same books to restore consistency on those two models, then it does absolutely nothing, because it knows that absolutely nothing needs to be done. And I could give the entire rest of the talk on other properties that you would like to have of a books, for example, the properties that relate to the intuitively simple idea that a bidirectional transformation shouldn't change more than it must when it restores consistency. The idea of least change or least surprise, but I won't because I've got other things I want to talk about. So let's go back to our JUnit and Java example and look at a number of different possibilities for what it should mean for all to be well. So we could have a very loose notion of consistency between our Java and our JUnit. We could just say we will consider them to be consistent if the files compile together without any errors. Or we could say we want that, and also we want that the JUnit file includes a test for all public methods in the Java. Or we could want even more than that. We could say we won't count them as being consistent unless it's also the case that all the tests pass. Or we can go even more stringent and say we want all that, and we also want that a certain coverage criterion is met. So there's no right answer about what consistency should mean between Java and JUnit. It's just a question of context. What is the appropriate thing to have in the context we're trying to facilitate? Of course, the more stringent our definition of all is well is, the more information we will be able to give to the user of the books about how confident they should be that they're in a good state to continue with development if the books reports that all is well. On the other hand, we're also taking a certain measure of flexibility away from them, in the sense that if they're in a setting where they insist that the books reports all is well before they continue with development, that means that they are kind of hamstrung. They are unable to sort of creatively tolerate inconsistency for a while without giving up on the use of the books. And naturally, the more stringent your definition of consistency is, the more difficult it is to write a books that will automatically restore consistency, which you can see as being a downside, but on the other hand, of course, that potentially saves more work for the user. And so it's all a question of horses for courses. Now we can, and sometimes we might want to, separate the tasks of checking that all is well and fixing it if it isn't. We can work with books that have a rather more refined notion of what consistency is, they can report that not just that the models are consistent or inconsistent, but they are this much consistent or consistent in this way. And we can have books that don't fully restore consistency. They might have properties such as at least making matters no worse. And that can be useful if you're in a situation where you want to share out the work between an automated books and a human developer. For example, you might want to say, I want to automate the propagation of uncontroversial changes where it's obvious what we have to do to propagate them, but in difficult cases I want to appeal to the user to do that. And I started to explore that in that phase paper listed at the bottom there, and it's coming back into focus for me just now for some future work, but that's all I'm going to say about that right now. So thinking bidirectionally buys us separation of concerns. The idea is that we end up with individual models, each of which records all and only the information needed by its group of stakeholders, and as a separate and different concern we have the process of reconciliation between those models. And separating concerns in this way can be beneficial even if we don't automate anything about the checking and restoration of consistency, especially because these concerns really require different skill sets. And this is especially so as we start to parcel more decisions out to more diverse groups of stakeholders. You may well have a group of stakeholders who are perfectly well able to use their particular model and really not at all in a position to undertake the job of reconciling consistency between their model and somebody else's model. So that's bidirectionality, and at this point I claim we can answer the question, yes, bidirectionality is important. But I haven't finished my talk yet, so let's go on. Full disclosure is that after you've worked in books for a while, you do start to feel that everything is bidirectional. And maybe it really is. I'm sometimes tempted to say that maybe relations and their restoration are actually a more fundamental notion to computer science than functions are. But that's a big claim and I'm not ready to defend it right now, so let me just drop that in and move on. We said that what made a thing important was that it needed attention. So now let's turn to, more precisely, what should we be paying attention to in the world of bidirectionality? Well, these are a few of my favourite things. I stopped putting things onto this slide more because I ran out of space on the slide and patience to try to make Tixie do what I wanted it to do. If anybody knows how I can make those crossbars not be grey, I'd like to hear from you. But here are a few of the things that I've been thinking about recently and still want to think about more in the future. So the big one over here is languages in which to express bidirectional transformations. And I noticed that the aspects of languages that I've listed here are almost disjoint from the set of aspects of languages that I listed in the paper, and that's really indicative of the fact that I think the space of bidirectional languages and what makes a good bidirectional language is really wide open at the moment. There are good things in the community, in the model-driven development community. There are good things in triple graph grammars and the tools for those, and there are good things in the OMG standard language QVTR. And in the programming language community there are languages like Boomerang and Beagle which have good properties, but I think we're nowhere near the level of understanding for bidirectional languages that we have for unidirectional languages, and we're in a phase where it's really important to let 1,000 flowers bloom and continue to explore that space. Bidirectional transformations relate domain-specific modelling languages, and Marcus Völter earlier on this week talked eloquently about the challenges in developing good domain-specific languages for people, and I think there's another set of challenges that goes along with saying what is it to be a good DSML that's amenable to being connected with other DSLs via bidirectional transformations that will repay further study. The process of specifying bidirectional transformations, having logics for them and verifying them, is an issue which I'll come back to briefly at the end. Recently I've been looking at certain aspects of bidirectional transformations in sensitive environments, for example in contexts where you want to keep certain information about the development process confidential, and you might be able to use books to, or couple of books to use that. I'll come back towards the end to talk briefly about ethics. But for now I want to spend a few minutes talking about something that has been on my mind particularly for the last year or so, which is the use of bidirectional transformations not just between two models, but in megamodels, what I've been calling books in the large, because I think this raises a collection of particularly interesting problems. Some of you have seen earlier talks of mine in which I've said that this picture is now my standard picture and has to appear in every talk that I give. I'm not sure how long I can keep this up, but I'm not tempted to stop it at this particular time, because what's being represented here is a development in which there are more than two models being used. So perhaps this red group up here might be a group of people working on a database schema, and perhaps this group of blue people here might be working on some kind of user interaction model, and this group down here appear to be working with Greek letters, so they're probably mathematicians of some kind, maybe they're safety engineers working on safety properties of the system. And these coloured wires are the bidirectional transformations. So these have the job of bringing together the current states of all of these models, reconciling them, so updating the models where necessary to bring them into consistency, and bringing all three of these models into consistency with a thing we can see as a fourth model, namely the actual running software itself, parceling that out to its users. Now once we have more than two models going on, we're in a situation where we've got a mega model which describes the different models that exist and the relationships between them. And here is a small snapshot from a real one. You can't really read it, it doesn't matter, you don't need to. This is the AutoSAR mega model, and the references in the paper, I hope. It's in last year's models paper anyway. All I want you to notice about this picture at the moment is that even though I've only given you a small snippet, there are a lot of models here, that they are related two at a time by binary bidirectional transformations, and they're all labelled with this OO. OO stands for overlaps, and the idea here is that we're in the situation which is the normal situation, where the models at either end of a bidirectional transformation record overlapping information. So it's not the case that one of them is a strict abstraction of the other. It's the case that there's some information which is shared between them, and each model includes some information which is not present in the other, roughly speaking. So in order to discuss the problem, let's take a small mega model, but just big enough to bring up some interesting issues. So the idea here is that we have a meta model, the UML meta model, let's say, and we have a UML model, and so the relationship at the top here is supposed to be the ordinary conformance relation between a model and a meta model. Here we have a standard round-tripping relationship between a UML model and some code that's supposed to implement it. Here we have a slightly more interesting ternary relationship, and in the models paper where I introduced this, what I was trying to do was to illustrate the fact that the state of one model may have an effect on the desired relationship between two other models. So the idea here is that we have some code, we have some tests, just as I've been talking about, but here we have a safety model which maybe records a whole lot of information, but part of what it records is, let's say for simplicity, just a Boolean that says, is this system considered to be safety critical or not? And we'll say that if the system is considered to be safety critical, then we want the relationship between the code and tests to be that the tests have to satisfy a certain coverage criterion over the code, in addition to whatever else we want to insist on. The first question I addressed in this models paper reference down there is one about whether we would like our ideal future bidirectional transformation language to have multi-re syntax. That is, should we provide syntax that enables the bidirectional transformation writer to write explicitly about relationships between more than two models at once, or does it suffice to make the semantically simpler language design decision and say that the transformation writer can only ever relate two models, and when we want to relate more than two models in a mega model, we need to write collections of binary bidirectional transformations? And to cut a long story short, the conclusion I came to is, well, it depends. If we insist on fixing the set of models and fixing the consistency definition precisely according to the requirements that we gather, then we do indeed need multi-re syntax. But if we're prepared to add extra models, or we are prepared to refine the consistency relation and thereby develop to a relation that's rather more stringent than the one we actually gathered, then we don't need to. And so provisionally, my conclusion is that using binary bidirectional relations is a reasonable choice, not least because they are cognitively easier to work with. I think in practice, if we start thinking about consistency relations between more than 3 sets, we have a tendency to comprehend them by projecting them onto pairs anyway, so we may as well work directly with the pairs. That's all very well for the consistency relation itself, but what about restoration? So the consistency restoration problem is now to say, if we're given a network like that, we're given some models which are connected by some binary bidirectional transformations, can we find a sequence of applications of the consistency restoration functions that have been already programmed and come along as part of those binary bidirectional transformation functions, such that that sequence will completely restore consistency in the model. It'll restore all the binary consistency relations. So here's a little example. I'm using dark here for authoritative models, which is to say those which are not allowed to be modified in the process of restoring consistency to the network this time. So this represents the idea that we're supposed to restore consistency between these 4 models. We are not supposed to modify the UML metamodel, no good can ever come of that, and right now we're also not supposed to modify the tests, perhaps because they have just been reviewed and it would be too much of a pain to change them right now. And we've got consistency restoration functions as shown. Don't worry about the super source, but this simple example is already enough to illustrate various problems. So the first thing to notice is that both the model and the code are impacted by 2 different binary bidirectional transformation relations, which means that in principle we have a problem requiring some extra intelligence to integrate those 2 kinds of consistency, to decide, for example, when there's a conflict, which side should win. And we also have a choice about which way certain bidirectional transformations are going to be used. Are we going to restore consistency between the model and the code by allowing changes in the model to win, or by allowing changes in the code to win? So some choices have to be made. Typically, even after we've made those choices, it still might be impossible to restore consistency, or the result we get might depend on how we choose to restore consistency. I started to explore in the paper a particular case where we're in a simpler situation because certain choices don't matter, and that's represented by the pink here. If we're in a particular situation where these bidirectional transformations impacting on model, having made the decision to use that one in that direction at this stage, are what I call non-interfering, they commute, then we're in a particularly simple situation, and we can say, well, we can restore consistency in this network by applying that, and then that, and then that, or that, and then that, and then that, and we'll have confluence. The 2 things will come to the same result. By the way, even in this special case, we still don't actually have confluence unless we've also got history ignorance of these bidirectional transformations, which we don't in general, but I won't go into that. So I think I misspoke a moment ago, never mind. So in other words, in this setting where we want to restore consistency in an entire network, we have a number of limitations. Sometimes there simply isn't a way to do that, there simply isn't a solution. Sometimes there is a solution, but not one that you can reach using the consistency restoration functions that come along with the binary bidirectional transformations that we've got. And almost never do we have confluence, in other words, a result that's independent of how we got it. And so I didn't like that situation much, so I wondered what we could try instead. So in some recent and ongoing work, I wanted to think about how to tackle in particular the impossibility of achieving confluence in realistic situations. And so I started to ask myself, where is the knowledge about how to satisfy multiple bidirectional transformations simultaneously, how to reconcile those various choices? And the answer is it's really there, where they meet in the model. And so I started to explore the idea of having a pull model rather than a push model, in which, rather than saying we'll restore consistency to the whole network when a change happens, we'll push the change out to the whole network, we would rather say, okay, now I want to use a particular model in my network, maybe I want to use the tests or something. So now what I would like is to say, before I start making today's edits, I would like to first bring my model into consistency with all its neighbours, and pull the relevant changes into my model before I start. So I found that there's some very useful stuff we can learn from the people who've worked on conventional software build systems, and I like especially this Pluto build system by Sebastian Edvek and colleagues, which enables us to encapsulate the job of reconciling different bidirectional transformations in what we call builders of the models, by adapting that work to our setting using an orientation model which manages which models are authoritative right now, and also in which direction we want to apply bidirectional transformations. And that orientation model is a model like any other and can be managed as a model, and changes to it can be managed in the same way as changes to other models. So I think that's a really interesting strand of work which I want to continue with. It's all I'll say about it right now. You can find early software in a paper draft at that URL, and by the way also a talk from the BX workshop on my YouTube. So if we can make progress on all of these problems, we open up a vista of what we might call deliverable models, in which instead of delivering a piece of software to our stakeholders and saying, well, we really hope we've captured all your requirements correctly, and if not, you have to come back to us and we'll modify the software for you, we would instead deliver a collection of domain-specific modelling languages, perhaps with an initial model in each of them, to the customer, saying, well, we hope that we've captured your requirements, but we're pretty confident that we've captured the kinds of requirements that you have, and so here is the modelling space in which you can vary the behaviour of the software by modifying the model within this domain-specific modelling language away from the initial state that we've delivered it to you in. And the effect of this is that we move more of the decisions about how software should work away from software specialists and to the stakeholders, thereby giving people more of a direct manipulation approach to how their software behaves. And that, I think, would really be a major advance in software engineering. That's how we make further progress on requirements and maintenance. We hand them over more to the people who are actually in a position to know what they want to do. But it's hard. It's very, very hard from many different angles, not least because those people are not software developers. They're not going to debug stuff the way that we assume that our software specialists will debug stuff, and the task of actually giving them languages that they can really in practice use effectively without needing to go to software specialists for every little change is something that we need a lot more work on. But lest you think that this is totally fanciful, let me point out that we already have it to a certain degree, in the sense that the software that people use all the time very often comes with a settings or a preference screen that people can use and are used to using in order to change the behaviour of their software. And that, of course, is nothing more nor less than a model that they use to change the behaviour of the software to their liking. So in some sense the question is not whether we can do this, it's to what extent can we do this, how expressive can these domain-specific modelling languages that we deliver to stakeholders actually be. So bidirectional transformations in the context of today's software engineering challenges is far from a solved problem, and there's lots of interesting work that still has to be done, and I could go on ad infinitum, but for the last few minutes let's be even more speculative. When I came into software engineering, the understanding had been reached in the community that the early idea that software would be developed to formal, precise specifications that would be fully verified was impossible for a variety of reasons. It was impossible to develop formal specifications of the software behaviour, but even more so, we didn't have the technology to do the verification, and even if we had, we didn't have the hardware powerful enough to do those verifications. But this aim of having full, precise, verified specifications of software has been experiencing a resurgence in recent years, in response, I think, to the great strides that have been made in the technology for doing that. And therefore a question naturally arises as to whether these bidirectional transformations that we should be developing should themselves have full, precise, verified specifications, and what that would actually mean. Well, the problem is that the mountain of challenges to such an approach rises, I think, still even faster than the technology improves. So let's look at it in our setting. Supposing we're in a position where we are delivering software in the deliverable models way that I just mentioned. How does formal specification of the system as a whole actually work there? So the moment a user modifies their model, they have modified, well, what have they modified? Have they modified the specification or the implementation or both? Well, we could end up saying, well, they've modified the specification and the Books' job is to automatically make the implementation match that specification, but I think that's kind of a cop-out, because the end-to-end properties of the system that we might imagine ourselves wanting to verify will not jump out of an individual model like that. But even harder, I think we are in the process of fractalizing the interfaces between our software and the environment and the humans who use them, so that the sense in which my model is an abstraction of the overall behaviour of the software may be obscure to me. Particularly if the Books incorporates machine learning, say, I may feel as though, although I have a model and I'm using it to influence the behaviour of the software, I'm more kind of giving instructions or hinting about what I would like the software to do, and I'm not necessarily being heard. So this is a very challenging problem. And we might be tempted to say, oh dear, it's too hard, we have to give up again. But let's give a counter view to that. So, how does interacting with humans work? Well, think about a human that you enjoy interacting with to get things done. Maybe that's a colleague, or maybe it's an administrator in your department, or maybe it's a member of your family. If that's too hard, think about one you just tolerate. Well, why does that interaction work well for you? Is it because you have a full, precise, verified specification of the behaviour of that person? Well, of course it's not. Although I have to say I love this quotation from Tolkien. You could tell what a Baggins would say on any question without the bother of asking him. Let's think a moment about what makes it work to interact with humans. Well, fundamentally it works because we're a social species and we've evolved to be able to do this. So we know how to have repeated interactions in similar roles with people and to make use of those repeated interactions to learn, for example, about one another's habits and principles and boundaries, the things that we will definitely not do and might do and try to do. And in order to enhance that understanding, we're able to use this fantastic mechanism called talking, which lets us get explanations of past behaviour when we're confused, and sometimes even to negotiate future behaviour. So in summary, usually, provided I know you quite well, I can predict quite well what you'll do, and if you surprise me, I'm not completely stumped, I know how to go on. So, what would it be to develop habits and principles and boundaries for our software, in particular for our bidirectional transformations? So I alluded earlier to the fact that non-software specialists who are using models can't be expected to debug the bidirectional transformation, and so there's a danger that if the Books does something to surprise them, they will be very stuck. And to the fact that I think this is even more so as we go on to fractalize the human-computer interaction and to make the interface there more and more complicated. But that should be okay because we don't debug one another, right? So what do we do? What would it take to make interacting with software as natural as interacting with a human? So maybe we should have some kind of idea of boundaries, namely things that the software will never violate, that we can rely on. principles that the software will always try to adhere to, and habits, things you notice that it usually does. Now, a lot of this sounds quite a lot like a high-level specification, or we might say here like a model, but some things are important to notice. One thing is that all of these things are approximate. So we don't expect that humans will absolutely always do the things they're in the habit of doing, but we do expect that they can probably explain exceptions if we are confused and we ask them to. And this kind of specification is a kind of specification that should probably evolve as time passes, including by negotiation. When something goes wrong, we should be able to say, oh yeah, actually, you should do it differently next time. And another aspect of it is that these things may not actually be articulated in advance. It may be that they get articulated as part of the process of explanation only when something goes wrong. So I think this is an interesting area to look at. Explanation of past behaviour. It's a hot topic in AI, of course, with the explainable AI movement. An explanation, it's going to be a bit like a proof, but different. It's a bit like a trace that we might use in debugging, but different. It's a bit like a justification that they have in ontology, where they talk about the collection of axioms that contributed to a proof. It's going to need to be comprehensible to the various people who are expected to be able to use an explanation. It's going to have to be tailorable to their needs. It's probably going to have to be interactive in order to achieve those things. I think games are a key technology there. But in the end, somehow, the computer needs to be able to answer questions like, what led to that behaviour that I found surprising? What were you paying attention to when you decided to do that? What principles applied? And perhaps most helpfully, what would have happened if something different had taken place? So I think there's a lot of interesting work to be done in that area. Negotiation of future behaviour in some ways sounds even more challenging, but let me bring us down to earth by giving a really basic example of a bidirectional transformation that remembers what you tell it, so that you don't have to tell it the same thing more than once. You don't have to read this Haskell, although if you can, be my guest. It comes out of that paper there at the bottom. The idea of this dynamic books, as we called it, is that if the current state of two models is that the left-hand one is A and the right-hand one is B, and we ask the books to restore consistency by giving it a new model A primed to go on the A side, so it has to modify the B to bring it into consistency with A primed. What it's going to do is it's first going to check whether it already knows how to restore consistency between A primed and B, and if it does, then it will just do that. And if it doesn't know yet, then what it will do is it will appeal to this function with which it's been parameterized, which will help it to work out how it should restore consistency in a new situation that it's never seen before. Now that function can do anything we like, provided that it has the right type. It might, for example, go and interact with the user by either asking them to build a consistent model out of whole cloth, or by choosing from a variety of candidates which they think is best. And in either case, perhaps it will check that the user has really given them a decision that does in fact restore consistency, and having produced that B primed, it will store it for later use, and so it'll never ask the user to solve the same question twice. Now, of course, this is a toy example. Replacing models in their entirety with new models is not going to work for models that are much more complicated than integers, but I hope you see that the general principle can apply in more realistic situations too. You can imagine having a bidirectional transformation that incorporates the information that humans give it from time to time in its understanding of the situation, and gradually gets better at restoring consistency between more and more models, so that it needs less and less interaction with humans. And I think this is a very promising area. But it brings us into areas which also incorporate a number of very challenging ethical problems. Right now, ethics for autonomous vehicles seem to be a hot topic, but I think we're going to see it even more so in this kind of area. So the essence of bidirectionality is that we are reconciling models that are simultaneously live and not orthogonal, and that involves reconciling the interests of different people. And right now these things are being done by comparatively dumb bidirectional transformations, and almost all the people involved are software specialists. But if we want to change that by parcelling out those decisions further away from the software specialists, will we end up with bidirectional transformations that can do what I mean? Will they kind of impose a power structure in the sense of imposing some kind of priority order between the preferences of one group of stakeholders and the preferences of another group of stakeholders? Will they kind of infer what that power structure is from the way in which people interact with it, for example, to reconcile different situations in the way that I had on the previous slide? Will they end up determining it in a way that we might not necessarily understand or want? And the way in which an essentially adversarial environment can impact all this will, I think, need very careful attention. We also, by the way, can't get out of jail free by just saying, well, whenever the transformation encounters a difficult situation, it should just stop and do nothing and appeal to a human, because that situation isn't going to be a solution after the rubber hits the road. We're surely going to end up in a situation where the transformations will have to do something, and we'll be left with the problem of determining whether that was the right thing. So, how are we actually going to manage this? Are we going to end up with a situation that works for the humans involved rather than against all or some of them? And this is going to be important and difficult, because just turn it off or stop using it is not going to be a good solution in the situation where the software we're talking about is the stuff that manages these really important interactions between different humans and the environment, like our heating and cooling and transport and food production and all the rest of it. It's not going to be like when your companion robot upsets the cat. Turning it off is not really going to be an option once we really start relying on this stuff. So we need to think about ethics, I think, sooner rather than later. So in conclusion, bidirectionality is about having transparent, predictable, controllable, dependable ways to reconcile competing interests, perhaps many of them, in order to build software that supports cooperation. So this is an important, difficult problem now, and I think it's only going to get more so. So I think bidirectionality is important, and also very interesting, to us as software engineering researchers. But I said at the beginning that I was going to come back to the issue of our roles as other than software engineering researchers. So let me finish with this picture. I'm not sure quite how far I want to push this analogy, but let me explain the picture a bit. What you just see in the background there is Arthur's Seat in Edinburgh. So Arthur's Seat is an extinct volcano. You can think of it as being a very large volcanic grindstone. It's fun to go and climb it, and you can even put your nose to it if you like, but we mustn't expect to have a huge impact on it very fast. It reminds me of that story of the bird that flies up to the mountain every 100 years and scrapes its beak against it, and when the mountain is entirely worn away, the first second of eternity will have passed. So, however much we like our work, and we should like our work, of course, we mustn't postpone life until after the work is all done, until after the grindstone is completely worn away. I think it's really important to remember to enjoy the grass and the trees and the sky as we go. And by the way, I think we will also do better work if we do that. So enjoy investigating bidirectionality, which is important, and remember to enjoy the rest of your life too. I'll stop there.